Hello everyone, welcome to the channel. So in this video, we want to examine how the image of the Earth's surface are recorded. So in our previous video, we have looked at the types of platforms that are used to carry the remote sensing instruments. So we now wish to look at the instruments, technology themselves, and those that are commonly employed. So that is we're going to focus in this video. So the Earth imaging could, of course, being carried out by mounting a simple digital camera on a platform, and today that is often done with the drones. Many of the earliest images of the Earth taken by the astronauts are captured by film cameras. And in the first three of the Landsat satellites, a television camera was used. And it was called Return Beam Videocon. And the RBI, that is RBV, represents the Return Beam Vidicon. And the Return Beam Vidicon was one of the two primary imaging instruments. The most remote sensing satellites today carry scanners of one form or another to capture the images of the Earth's surface. They tend to make use of the forward motion of the platform along with some form of scanning either across or along the path of the satellite in order to build up an image of the landscape. So we're gonna look at three types of scanners or in this video. So the first scanner will be our line scanner, and the second type of scanner it is push broom scanner, and the third is the hyperspectral scanner. So the first scanner it is the line scanner. So the earliest digital imager was the line scanner, a technology which is still in use today. It uses the mirror to scan across the path of the satellite, as shown in the slide, in order to focus the strips of the Earth's surface. So you can able to see here onto a detector carried on the platform. So by design, the rate at which the mirror scans and the forward velocity of the satellites are arranged so that a consecutive scan lines are adjacent to each other, and together form an image as a satellite traces out its path. So here in the line scanner you can able to visualize the diagram here. So here you can able to visualize this is our rotating or oscillating scanning mirror. So this is the part of rotating or oscillating scanning mirror, and you can able to see the several parts here. So here in this part of the portion that is FOV, that is called as a field of view. So the FOV is defined as a field of view, the full width of the scan, which corresponds to the swath width of the image. And next is a IFOV, so that represents our instantaneous field of view, the smallest detectable element on the landscape. So in the line scanner, you can able to see that. So the each of this, you can able to see here, the each of these consecutive scan lines are composed into a picture. So for example, first it scans this particular line and the image forms in this particular row here, and followed by a next set of scan will be done in this portion of the region, where the next set of image will be formed in this set of row here, and followed by the third scan where the mirror oscillates towards in this portion of the area, and it forms the in the third row it forms the other set of images here. Let me explain it once more time. So the mirror has to oscillate from side to side. So mirror has to oscillate from side to side. So to create a image using this particular line scanner, so it has to scan each of this. The mirror has to oscillate along each of this row. So to form a complete image, so it has to first scan this particular row, and next it scans the next set of row here, and in next set it scans another set of row here. As a result, the image formed in the line-like format. The first it forms in this way, and after that the next scan a next set of row of image will be formed, and in the next set of another row of image will be formed here. And this particular green square here represents the pixel, so it is comparable with this image here. So this particular square represents the pixel, and this particular square in the image represents the pixel. So in sensors like Landsat multispectral scanner, the upwelling radiation from the landscape is detected on the forward scan of the mirror. The mirror then resets to the opposite side of the satellite track and ready for the next scan. By contrast, the Landsat thematic mapper and its later variants records the data on both the forward and reverse scan. Sometimes, particularly in early aircraft sensors, a rotating mirror is used. And this particular slide also introduced some important definitions. So first, the width of the image recorded is called swath. So here you can able to visualize it. So the width of the image recorded is called as the swath width. It is defined by the field of view, or FOV, of the sensor, which is the total angle over which it scans. The resolution of the sensor, or the scanner, is called as instantaneous field of view, or IFOV. And again, this is defined by the angle which when projected onto the surface defines the pixel size in, or the spatial resolution of the recorded image. Most often, the IFOV is the same in the along track and across track directions. The mechanism described in accounts for the scanning process. So this image shows a basic mechanism of this scanning process. But most remote sensing imaging instruments are capable of recording in several wavebands simultaneously. So the remote sensing imaging instruments are capable of recording in several wavebands. So you can able to view from this image here. The most of the remote sensing instruments are capable of recording in several bands. For example, here I have shown you the green, red, and blue band. So with the line scanner, that is achieved by placing a dispersive element in the path of the radiation. So here the dispersive device is this particular a prism, or a diffraction grating. So a dispersion device such as a prism or diffraction grating integrated with a sensor separates the recorded signals into a number of wavebands by dispersion the radiation onto a set of detectors. There are as many separate images recorded of the region, Earth's surface, as they are the detectors and thus the waveband. So the dispersion device that can be a diffracting grating, a diffraction grating, or a prism, the effect of which is to break up the incoming beam into individual beams corresponding to the waveband of interest, and those beams are then focused onto a separate detectors, one for each waveband. So now the next scanner is the push broom scanner. So another a common means for forming an image is to use a linear array of individual detectors arranged across the direction of the satellite motion. Usually this is a CCD, or charged coupled device array, with one element for each of a series of longitudinal scan lines, that is scans line along the track of the satellite. So here you can able to visualize from this image. This is our push broom scanner. So this is our a linear detector array with one detector per pixel across swath. So you can able to see here. So this linear detector array, which images the whole lines of pixels simultaneously, you can able to see here. This set of linear detectors which images the whole line of the pixel simultaneously. Here you can able to view here, and the platform motion is towards this direction. So sweeps out of an image. So first it scans this set of row here, the entire row here, and next set of scan, it scans the entire set of this next set of row here, and moves the scan is towards the longitudinal motion towards this direction here. So the radiation falling on each detector is sampled in time, allowing the pixels to be formed. The pixel size is defined by the detector's instantaneous field of view at the surface, and the rate at which the radiation is sampled compared with the forward velocity of the platform. So no mechanical scanning is involved apart from the forward motion of the satellite. So the advantage of the push broom scanner technology is that more radiation can be gathered per effective pixel in allowing a higher spatial resolution to be achieved. And again here you can able to see a dispersive device is incorporated. So you can able to view here, this is our dispersive device, and to allow the simultaneous recording of several wavebands. and there will be a separate detector CCD array for each waveband. So now our third scanner is Hyperspectral Scanner. So perhaps the most recent imaging technology used on the spacecraft and aircraft platforms is similar to the push broom concept just we have discussed earlier. But instead of having a separate set of linear CCD array to record a discrete a set of different wavebands, a two-dimensional CCD array is employed. So here you can able to view from the image of a hyperspectral scanner here. So this is a two-dimensional dispersive device being used in this particular scanner. The second dimension is used to record, that is used to replicate the effect of a very large number of separate linear CCD arrays. So in this manner, a number of wavebands recorded simultaneously and can be very large. So typically up to 200 or so. Therefore, this census typically records simultaneously several hundred carriers of images of the landscape ranging over the visible and infrared wavebands. So here you can able to visualize the hyperspectral scanner. These are the different parts here. So its working is comparable to the push broom. So instead we are using the dispersive device. It is the two-dimensional dispersive devices we are using. So as we will see in the later section that will allow a great deal of information to be obtained about the landscape being imaged using this particular scanner, that is hyperspectral scanner. So when the number of recorded wavebands is small, say 20 or lower, as for the two previous instruments we have seen, the device these devices are typically called a multispectral scanners. So the line scanner and the push broom scanners are called as a multispectral scanners. Similarly, when the number of wavebands can be in order of 100 or so, and these instruments are usually called as hyperspectral scanners. So now let us go through the technical characteristics of the image data. So now that we can see how the image can be recorded, we can summarize their important properties when used for remote sensing purposes. Recall first the geometric property of the scanners shown in the bottom of this slide here. You can able to view here. So here the IFOV of the scanner defines the spatial resolution or the pixel size on the ground, whereas the FOV of the scanner defines the swath width. So the FOV here defines the swath width. And also shown in this diagrams are the typical units used to describe each of those properties in the practice. So here, so this particular diagram here are typical units used to describe each of those properties in practice. So here, this particular image, we have summarized how the image in the remote sensing is described. Overall, it is defined by the swath width in a cross track direction and the frame size in the along track direction. Most often, particularly for operational missions, the frame size is chosen to be same as the swath width. So the next important feature is the pixel size. So you can able to see here, there is a pixel size. So which determines the level of details about the Earth's surface being recorded. As indicated previously, we often refer the pixel size as the spatial resolution of the image. Clearly, we are also interested in the number of wavebands being recorded. So as indicated here, the wavebands are registered with each other geometrically. You can be able to see that there is a number of wavebands. So consider this is waveband 1, 2, 3, 4, 5 and 6. So all these wavebands are registered with each other geometrically. And finally, we need to know the number of brightness level available for each pixel. So we're gonna take this particular thing here, the number of brightness level that is available for each pixel. So for a black and white image, those levels will be the graduations from black to white. So you can able to see here from black to white. In fact, any image recorded in a given waveband will effectively be a black and white image representing a level of received radiation from 0 to a maximum sensitivity of the detector. So I can able to view here from 0 to the maximum sensitivity of the detector, that is represented as n minus 1. So n here represents the discrete brightness level. So in the later section, we will see how we display those recorded bands in color. The number of brightness values available per pixel is defined by the binary arithmetic. So for example, 8-bit pixel is capable of representing 256 levels of gray from 0 to 255. So the 8-bit image can represent 256 levels of gray starting from 0 to 255. The most current operational remote sensing images will have 8 to 10, 8 or 10 or even 12-bit pixels. The number of brightness values are often expressed as a number of bits. Is called the dynamic range or the radiometric resolution of the sensor. So here you can able to view here, we can generally represent n equals to, n represents the discrete brightness level equals to 2 to the power of m. So here the m represents the 8-bit pixel, which represents 256 levels of gray, the gray levels, and similarly the 10-bit pixel represents 1024 levels of gray, and similarly the 12-bit pixel, which represents the 4096 levels of gray, and similarly the 16-bit pixel here represents the 65536 levels of gray levels. So the key points covered in this video: the satellite sensors can be of different types using oscillating mirror or CCD arrays. Those sensors could also be carried on aircraft or a drone platform. The sensors includes a dispersion mechanism that separates the measured radiations into a number of wavelength ranges or wavebands. The images are described by their coverage, the spatial spectral, and the radiometric resolution, and the range of wavebands they cover. The field of view, usually measured in degrees, defines the swath width being imaged, while the instantaneous field of view, usually measured in milliradians, defines the spatial resolution or the pixel size. So the important message from this video is the geometric characteristics of the sensors. That is the instantaneous field of view, the field of view, and so on, and the properties of the image itself. So in this video I have shown you how do we record images of the Earth's surface. So thanks for watching and please subscribe to our channel and give us a like.